Hey everyone, welcome back to Technical Professor. So this is the channel for AI and machine learning. Wish best of luck for learning. Let's start it. Have you ever trained a machine learning model that performs perfect in training data, but completely failed in real world? So that's not a bad luck. That is the bias variance trade-off. So one of the most important machine learning concept in machine learning. So in this video, we understand exactly why model fails and how to fix them. So let's get started. So hello everyone, welcome back to Technical Professor. So in this lecture, we are going to breaking a core idea that separate beginners from professional machine learning, how models generalize. So let's start it. So why generalization matters? Let's see. So let's start with a simple question. What make a good machine learning model? Good machine learning model. So most people say high accuracy, but that's only the half story. A model can achieve extremely high accuracy on training data, okay, and still perform terribly on unseen data. Why? Because it did learn patterns, it just memorized. Okay, why? Because it didn't learn patterns, it just memorized. This is the ability to perform well on new data is called generalization. It means how they can perform on new data. That is generalization. All right. So, and the ultimate goal of the machine learning. Okay. So, why gen? The first topic is why generalization matters. First one is model fails on unseen data and training accuracy misleading and introducing the trade-off. So these are the reasons why generalization matters. So machine learning models often struggle to generalize, leading to performance on new unseen data and training accuracy misleading means high accuracy on training data can be deceptive, not reflecting a model ability to perform well in practice. Okay. Then is introducing the trade-off. Understanding the bias variance trade-off is essential for improving model and achieving better predictive performance. Okay. So now, we are going to understand what are the concepts here. So first one is bias concept. Okay. We need to understand two kind of errors. First one is bias and variance. Bias is the error that is caused by or by simply assumption. For example, we assume this will be true. That leads to cause errors. Okay. And variance is the error caused by too much sensitivity to the training data. Think of like this. Bias is the model is too rigid and variance the model is too flexible. And both can hurt performance just in different ways. Okay. So let's talk about generation machine learning. It is perform on new data, avoid memorization, and capturing underlying patterns. So you already know generalization refers to model ability to perform on unseen data. It is essential for real world applications. And second one is avoiding memorization. So model must learn to recognize underlying patterns rather than simply memorizing trading examples to ensure effective generalization. And third one is capturing underlying patterns. The core goal of machine learning is to accurately capture the complexity of data, allowing for reliable predictions. So what is training versus testing? Let's see. So training error, it measures how well the model fit the training data, indicating potential overfitting it is too low. And testing error. In testing error, it affects the model performance on unseen data, and it is critical for determining the generation ability. And third one is gap analysis. The difference between training and testing errors reveals underlying model issues, needing adjustment for better performance. Now we are going to understand underfitting the undercomplex model. The first one is high bias. High bias occurs when the model makes strong assumption and leading to oversimplification and missing critical data patterns. And second one is low variance. Low variance indicates that the model prediction are consistent across different data set, but often at the cost of flexibility. And third one is poor performance. Underfitting result in poor performance on both training and testing dataset as the model cannot capture essential trade-off. So now we are going to understand our fitting. Style this. So overfitting. Overfitting is low bias, high variance. Overfitting occurs when a model captures noise rather than the underlying trend. It is resulting in high variance. And second one is model complexity issue. A model that is our like complex ways to generalize well, but other often fitting noise and outliers in data. That is model complexity issue. And third one is poor generalization. This lead to poor performance on unseen data, as the model is tailored too closely to training data. So now we are going to understand bias. It is simply assumption. Bias arises from our simplified assumptions. It is made by the model and failing to capture essential complexities within data. And our simplified model that are too simple result in high bias, leading to poor performance and missed patterns in the training data. And third one, risk of underfitting. When the model cannot adapt to complexities, it leads to underfitting, which severely limits to predictive capability and accuracy. Then, bias example. First one is linear model fit. A linear model fit fails to capture the underlying complexity of nonlinear data distribution effectively, and missed curvature. A straight line fitting result in significant errors as it overlooks crucial data patterns and curvature. And third one is high prediction error. The performance of the linear models on nonlinear data leads to high prediction errors and poor generation. Now we are going to understand variance. So, sensitivity to data. Variance means how sensitive a model is to fluctuating in the training data, it impacting its predictions. And second one is model instability. A model with high variance tend to exhibit instability, yielding a consistent result when exposed to new data sets. And third one is learning noise. Model at our feet often learn noise present in the training data, fail to generalize effectively to unseen data. And what are the examples of variance? First one is high degree polynomial. A complex polynomial attempt to fit every training data points, capturing random fluctuation and noise in the data. Okay, then second one is thought fitting issue. The result in poor generation as the model fails to perform well on unseen data outside training. And third one is visual representation. The scatter plot illustrates a weakly line that fit the training data too closely, it missing the underlying trend. Now we are going to understand bias versus variance. First one is rigid assumption. Bias arises from our simplified models that cannot capture the complexity of real world data and leading to errors. And second one is flexible models. Variance results from our like complex models that adapt too closely to training data and capture noise and fluctuation. And third is finding balance. The challenge lies in optimizing the trade-off between bias and variance to achieve the best generation in models. The trade-off concept. Trade-off concept is reducing bias, reducing variance, achieve balance. This is the trading trade-off concept. It means lowering bias typically involve increased model complexity throughout more features and flexible functions. And segments reducing variance. Lower variance often means simplifying models or using technique like regularization to prevent overfitting. And third one is achieving balance. Finding the optimal balance between bias and variance is essential for improving model generation on unseen data. Error formula. The error formula will be like the total prediction error encapsulate bias squared, variance and irre- irreducible noise affecting model accuracy, bias contribution, and bias variance contribution. You can see that bias squared measures systematic errors due to model assumption and which can lead to underfitting. This is very important, underfitting. It will lead to underfitting. And variance contribution is variance reflects sensitivity to data fluctuation and capturing noise that can result in overfitting and reducing generation. So now we are going to understand model complexity and error. First one is low flexibility models, high complexity model, optimal flexibility. These are the it often results in high bias, failures to capture essential patterns in data, high complexity also high variance causing to fit model fit to noise rather than underlying relationship. And medium complexity where bias and variance result in optimal U-shaped curve. You consider this one for generation is for optimal complexity. Now we are going to understand visualizing the trade-off. First one is training error decrease. As the model complexity increase, training error consistently decrease, indicating a better fit in the training data and U-shaped curve. And validation error for a U-shape initially decreasing and then increasing. It is illustrating the overfitting risk as the complexity rises. Optimal complexity point. There exists an optimal point of complexity where validation error is minimized and balance bias and variance effectively. Diagnosing high bias. High training error. Model with high bias shows significant error on training data. It indicating sufficient complexity to fit the data well. And high testing error. High testing error corroborates high bias, showing the model failure to generalize beyond the training data. And model simplicity. A simplistic model structure often leads to high bias, missing key patterns necessary for accurate predictions. Diagnosing high variance. Uh, Diagnosing high variance means low training error, high testing error, and model complexity. As what are the strategies for reducing bias? First one is employ complex models, add relevant features, reduce regularization. And in employ complex models, utilizing more complex model allows for better representation of integrate data patterns and reducing bias and improving functions predictions. And relevant feature also introducing additional relevant features into a model enhance its ability to capture essential data, characteristic, and relationship. And lowering regulation strength help the model fit the training data more, thus minimizing bias variance. So these are the strategies for reducing bias. And the first one is employ complex models. Second one, add relevant features. Third one is reduce regularization. So these are the strategies for reducing bias. So now strategies for reducing variance. The first one is simple models. Utilizing less complex model help in reducing the risk of overfitting and improve generalization. And second one is the diverse data. Acquiring the broad range of training data allows models to learn better patterns and reduce variance effectively. And third one is stronger regulation. Applying regulation technique and can help control the model complexity and reducing tendency to fit noise. Okay, so third one is the role of regulation. The first one is complexity control. Second one, variance reduction and bias impact. This they are the role of complexity control and regularization technique effectively control model complexity, promoting a simpler and more interpretable model structure. And variable reduction by introducing regularization models can significantly reduce variance, enhancing their performance on unseen data. These are the rule of role of regulation. And third, bias impact. While regularization may slightly increase bias, but it ultimately lead to improve generalization for the model. Cross validation overview. First one is multiple data splits, model stability evaluation, reducing variance bias. These are the cross validation review overview. And cross validation involve dividing the data set into several distinct subsets to ensure comprehensive model evaluation. And in model stability, this method tests model performances across different subsets, assessing how consistently it performs with variant data. Like if you're performing on unseen data, that it help to create model stability. And reducing variance also, and cross validation adds in minimizing bias in variance estimation, leading to improve model selection and reliability. Now we are going to understand train model, evaluate error, diagnose issue, adjust model. In train model, initial model training using selected algorithm data and evaluation evaluated error, assess training and testing performance to identify discrepancies and diagnose issue and identify bias or variance problem affecting model performance and adjust model, modifying complex or data to improve model accuracy. So, what are the summary of trade-off? Let's see. What key concept? We understand the various trade-off is vital and for enhancing model performance and achieving better predictions. Importance of achieving balance between bias and variance is crucial for effective model generalization on unseen data. What are tools of improvement? Regularization technique and divorce data are powerful methods to manage bias and variance effectively. So thank you so much for watching this video. We will you can comment and what you like about this lecture and what you learn from this lecture. So thank you so much for watching this video.